Hello. Hello. Welcome to our environmental seminar. I'm very pleased to introduce Jack Zweifel today. Jack started here at Wisconsin in 2017, not as a grad student. I'm doing the math on that. As an undergrad student in 2017. And got his degree in atmospheric sciences here, and I think he finished up most of his degree in actually 2021, but decided to continue on to finish also a degree in applied math in 2022. And then started in 2022 as a graduate student working with me on this problem of looking at seasonality of aerosols and their impacts in the climate system. I first met Jack in 2019, actually probably before then, but 2019 when I was teaching AOS 330, and Jack was my student there. Despite doing just fine in the class, Jack would be in office hours every week, asking very probing questions, and it occurred to me very early on that Jack and I both share an interest. If there's a rabbit hole, we're going to dive into it and get down to the very bottom. So Jack is, one thing that's always impressed me about Jack is his interest in understanding things to the nth degree, back to first principles. And so it's been very fun working with him in that respect. Jack, we started working on this problem and then developed some numerical modeling for this. And then over the summer, Jack went down to Oak Ridge National Laboratories in Tennessee to work with some collaborators of ours on this DOE project, including developing machine learning, or beginning to develop a machine learning emulator for RRTGM, the rapid radiative transfer model for GCMs. So it's been great working with him. This is some of what will go into his master's work. Most of what's going to go into his master's work. And I'll let you take it away from here. So,
okay. Is the microphone on? Seems like it is. Mm-hmm. Okay. Hi, everybody. Yes, my name is Jack. I think probably all of you know me, and I'll just repeat the things that Dan said. Yeah, I was a former undergraduate student in this department, current graduate student in this department, and I'm here to talk to you today about some of the research that's gone into my master's thesis in a presentation I'm titling Investigating the Seasonality and Radiative Forcing of Anthropogenic Sulfate Aerosols over the North Pacific Ocean. It's kind of a mouthful, but I think that this actually intro slide is a really good one, where we can look in the background. I found this really great NASA's reanalysis data that's combining, a global atmospheric model with some hourly satellite data to produce fields in sulfur dioxide and sulfate aerosol. So this is kind of just perfect for what we're going to look at, and it's also eye candy to some extent. But I think it's also worthwhile to see, this is real data, and seeing where do we see sulfur dioxide plumes in the world? Where do we not see them? How do they seem to relate to the plumes of sulfate aerosol that then spring up afterwards? You can see lots of cool things. You see some volcanic activity right there of Papua New Guinea, and you can just see all these beautiful traces of aerosol activity going on. Without further ado, we'll get into what we're actually talking about. So in my presentation today, there's going to be kind of 5 different parts to it. First, just looking at an introduction and background. Next, looking at our methods and model setup. Then kind of looking at the first part of our results of investigating seasonality in sulfate aerosol over the North Pacific. Secondly, looking at its implications for seasonal sulfate radiative forcing over the area. And then lastly, some broader implications and ongoing work that Dan had already mentioned. And so I say, let's just get started with the introduction and background. And I figured what would first be kind of necessary for this is to define what our regions for burden and forcing analysis in this research was going to look like. So I have that plotted here, where in this study, we're going to investigate aerosol emissions from East Asia. And East Asia we decided to define as kind of the conjoined emission masses that come out of China, Japan, and South Korea, as I have kind of highlighted there in the pink. So this region is going to serve as the studied and varied source of anthropogenic sulfate aerosols for our research. Secondly, we have our downwind region, which is defined based on the IPCC's most recent assessment report's North Pacific Ocean domain. But that actually domain goes all the way down to the equator. Here we decided to trim that to a bottom degree of 20 north, just to kind of focus more on mid-latitude effects and transport. And lastly, I'll just say that these domains are going to be applied consistently across our simulations, providing spatial anchors for evaluating both the sulfate burden and associated radiative effects. So anytime that I'm talking about East Asia, or I reference East Asia, I'm talking about China, Japan, and South Korea. And when I talk about the North Pacific Ocean, I'm talking about this hatched region right here. So I also figured it would be good to start right away and kind of jump in. We'll eventually pull back right after this, but really we're starting with what kind of the motivating puzzle for this work is. And that's looking at East Asian emissions and downwind burden in CESM's Lens 2 historical simulations. That's the large ensemble with historical forcing, where we're looking at total sulfur flux, which is kind of a measure of how much sulfur is being emitted out of East Asia, both from emission sources at the surface and aloft, where we can see an evolving and increasing profile of East Asian sulfur dioxide emissions from 1850 in pre-industrial times, where you can see we have really no scaled emissions at all, and that when we plot our monthly values together and track them, they're all kind of collapsed onto each other. There's no difference throughout the year in terms of what's happening, and we really don't start to see any of that until later. And when we do see that, we can see what you could maybe describe as a weak seasonal cycle, where we have more sulfur emissions in February and November than we do in, say, May and August. That can largely just be tied back to heating and energy demands that are required for that area at this time of the year. But then, what I think the really interesting part is, and really kind of the motivating puzzle of this, is looking at the downwind sulfate aerosol optical depth over the North Pacific Ocean. Here, we see this same historical profile in North Pacific aerosol optical depth, which is a measure of that you can use that kind of as a proxy for measuring how much sulfate aerosol is there, as it's a measure of extinction of solar ray by the aerosol optical, or by the aerosol, sulfate aerosol itself. And we can see here that there's a modeled seasonal difference. Already at the beginning in these pre-industrial times, we have much lower sulfate aerosol optical depth in the months of February and November than we do in May and August. And as our emissions have increased, all these seasons do reflect those enhanced emissions, but the spring and summer exhibit the strongest rise. As you can see, kind of we start to begin our large emissions somewhere between like 1950 and 1970. And so we can see this large track up of emissions, and we can see that reflected here. But when we look at how February and November evolve as compared to May and August, there's this growing divergence in this kind of building seasonality on top of what's already there from pre-industrial conditions. So that kind of motivates us to our research questions, which are, how do historical developments in East Asian sulfur dioxide emissions influence the seasonal cycle of sulfate aerosol burden over the North Pacific? And secondly, what are the radiative implications of these seasonal sulfate aerosols over the North Pacific? So like I said, that was kind of the drill in. We'll take a quick step back out. And I think most people here are familiar with this, but still we should talk about what are aerosols in general. This will be fast, but so far you can just think about aerosols as microscopic particles that are small enough that can be suspended in Earth's atmosphere, either solid, like we have right here, and these can have really vast, complex diversity in terms of their size. I think right here we're trying to look at, this is computer generated, but this is looking at black carbon particles that aggregate together into these chains and clumps, and then comparing that to just spherical droplets of some sort of liquid that's also suspended in the gas. And though these aerosols are often invisible to our naked eye, they play a critical role in influencing climate, weather patterns, air quality, and human health. Also, I'll just lastly say that these particles span a broad range of sizes from a few tens of nanometers to several tens of micrometers. I think this figure also does a good job of kind of pointing that out, relating how different aerosol sizes can be related in terms of something like a raindrop, which is really dominant in terms of size compared to those, versus something like a cloud droplet, where depending on the size of the aerosol particle itself, it may find itself larger or much smaller than even a cloud droplet. And we organize these aerosols into size bins like PM10, which is particulate matter that's less than or equal to 2.5 micrometers in diameter, PM2.5, and then even smaller, like these UFP, which stands for ultrafine particles. But we can do that and more. And then, yeah, John.
Can I ask you a quick question, Jack?
Of course.
Liquid aerosols, is there a mixing ratio of liquid water that is a threshold above which you call it a water droplet?
I don't know. That's a good question. I would guess it's mostly like a size-dependent thing rather than like a ratio in terms of masses. but I haven't looked at that
Okay,
yet.
all right, thanks.
So then going from just aerosols in general to sulfates, because that's what this paper is or that's what our papers and what our presentation is going to be about. So what are sulfates? I like this definition from NASA's Earth Observatory, which says sulfates are particulate matter that consists of compounds of sulfur formed by the interaction of sulfur dioxide and sulfur trioxide with other compounds in the atmosphere. In our work, we're going to kind of say that sulfates are a family of aerosols, a family of compounds that are kind of linked by this common ion, this sulfate ion, this SO4 2-. That'll kind of serve as the common bridge connecting things that we'll see like ammonium sulfate, which is NH4 2SO4, or hydrogen or sulfuric acid with this H2SO4 structure. So you can just kind of keep in your mind, even though these molecules are not the same, they both fit into our family of sulfate aerosols as kind of a parent. It's also important for us to look at what sulfate sources and precursors are. So I made this nice little figure for you guys, where we can see there's a variety of sources for these, whether they come from the ground. Surface-based sulfates come, both from things that you might think of like combustion in terms of combustion engines and transportation, but also a large amount of sulfur is present, and sulfate and sulfur are present from phytoplankton producing dimethyl sulfide. Then we also have surface but elevated emissions that come from more industrial and energy intensive reasons. And then lastly, as we saw before in that satellite loop, we saw that there's there could be volcanic activity as well, or when that erupts, like animation, when that erupts, you can spew huge masses of sulfur dioxide and sulfate aerosol into the atmosphere itself, so almost sometimes reaching all the way up into the stratosphere where it can really have a long residence time. But really, we're going to focus on coal burning as a major sulfate source here. I had to do a little bit of research on this because I had really kind of no clue what coal was. Coal, essentially, you can just kind of think about it as biological matter from millions of years ago that is decayed in these peatlands. That's where you're kind of old plants are decaying, in stagnant, low oxygen concentrated water, and with enough time and pressure and heat, eventually turn from peat into lignite coal, subbituminous coal, bituminous, and then anthracite. Each one, taking more time, pressure, and heat, and becoming more and more concentrated in terms of its carbon content, and gets darker, shinier, and it burns cleaner. But still, all of these have some level of impurity to them, and some of that impurity is from sulfur, which is the 10th most abundant element in the world. So when we combust this, and we burn that sulfur tends to mix with the oxygen in the air and creates sulfur dioxide. So we're not at sulfates yet, but we are at sulfur dioxide, which is going to kind of be the main player in producing these sulfates. You can kind of think of it as a sulfate precursor. So moving on from these sulfur dioxide molecules, we have sulfate formation. That's going to have two different avenues. One being dry production, where sulfur dioxide can react with hydroxyl radicals, these OH radicals, and produce H2SO4 or sulfuric acid. Visualizing that here, we can see that the sulfur dioxide gets reduced, or oxidized, sorry, and then it loses electrons to this oxidizing agent of hydroxyl radical, and then through some simplified chemistry, we'll eventually create these hydrogen or these H2SO4 molecules themselves. We also have aqueous production pathways where sulfur dioxide can react with ozone and with hydrogen peroxide to produce this sulfuric acid compound. Visualizing that again, we can see it's a very similar process where the sulfur dioxide molecule gets oxidized by these oxidizing agents of ozone and hydrogen peroxide in the same way it did with these hydroxyl radicals. But this often occurs in cloud, possibly in droplet. And we still create this sulfuric acid compounds that we can think of as sulfates. So that's how sulfates are created, and now we have to think about how sulfates are removed. There's really kind of no special way for them to be removed compared to any other aerosol. So there's kind of two different avenues again. One being through dry deposition, where this is kind of a slow process of the direct settling of these particles onto land or ocean surfaces, and this is driven by gravity and surface contact. And these are, kind of largely slower processes that happen to, what the aerosols themselves that are larger. And we compare that to wet deposition. This is, removal by clouds and precipitation, either through rainout or washout. And this is a much faster process, and it's very efficient at cleansing the atmosphere and plays a strong role in controlling the lifetime and transport of these sulfate aerosols. So that's kind of talking about aerosols themselves and what builds them up and stuff and their physical characteristics. But we also need to talk about their radiative impacts. And by that, I mean their relevance to climate in terms of how aerosol interactions alter Earth's atmosphere and energy balance. I like this figure right here. It does a good job of showing a whole myriad of ways in which aerosols can affect and play roles that are important in our atmosphere, whether that be emissions of dust or depositing some darker absorbing aerosols onto snow and ice cover, phytoplankton. That's kind of what we were talking about with that DMS from producing sulfate. And when we talk about the climate relevance, really that's going to lead us to talking about radiative forcing. And radiative forcing you can think of as the standardized metric for comparing climate impacts. And you can use this both to compare things like long-lived gases like carbon dioxide, those greenhouse gases, to short-lived aerosols like sulfates. So that brings us to looking at these historical radiative forcings. Here we're going to consult this figure from the most recent IPCC assessment report, where we look at change in effective radiative forcings from 1750 to 2019. We can see that well-mixed greenhouse gases like carbon dioxide, methane, and nitrous oxide have this positive radiative forcing, meaning that they are acting to warm the Earth system. And we can measure that, this is actually somewhat of a conservative measure, but still at 2.83 watts per meter squared. We also have, other greenhouse gases like ozone adding a positive forcing to this story at 0.47 watts per meter squared. We also have albedo-driven forcing changes, where we have changes in land use and reflectivity, where that can at some points be used to have a negative radiative forcing, but also, as we talked about earlier, depositing of absorbing aerosols on light and snow, or on light absorbing aerosols on particles of ice and snow that we can see here, like this black carbon that's deposited on this Arctic glacier. But what we really want to call our attention to here are the aerosols themselves. And these aerosols stand out as the clear negative forcing agent in comparison to anything else. It really dwarfs all the other things in terms of that. And when we look at it closer, we can see that there's also kind of two avenues in which aerosol radiative forcing is going to be present. That being through cloud radiative effects or aerosol cloud interactions, which is kind of the majority, and then aerosol direct radiative effects that we can see here. So you can see, this is kind of illustrating what some of these direct effects are. This is from the third IPCC assessment report, where we can see, there's examples of scattering and absorption, and then, some of a whole suite of these cloud-mediated effects, where there can be what's called the Twomey effect, where we can have increased cloud droplet number concentrations from having more sulfate or having more aerosol in the air to create more cloud droplet number or more cloud droplet nuclei, and then also having also the Albrecht effect, which is the second indirect effect, where we can have longer lasting clouds through suppressed drizzle amounts. And then the last thing I'll kind of call us to think about here is when we look at the error bars for this. We notice that the error bars for these aerosol radiative effects are much larger than anything else here. And that really kind of highlights the degree of uncertainty that we can think about, or that we have to think about when we think about aerosol impacts. This is a very hot topic in the aerosol community. I just chose a few papers at random to look at, just to kind of see, how overarching this is. Like this one that says, uncertainty in aerosol cloud radiative forcing is driven by clean conditions. This one, constraining uncertainty in aerosol direct forcing, a large uncertainty in future warming due to aerosol forcing, on the relationship between aerosol model uncertainty and radiative forcing. But I think the one that sums it up best is here. Aerosol forcing, it's still uncertain and it's still relevant. It's something we need to have further research into. So as we kind of get to the last part of our introduction, I think we should revisit this central puzzle again, because again, this will kind of be what's motivating us throughout the talk. And that, yeah, we have these, growing emission trends that we expect to see, and that they have a very explainable seasonality to it, and that seasonality, I would say, is fairly limited. But we have downwind in the North Pacific Ocean. When we look at sulfate aerosol optical depth, we have this historical seasonality that tends to grow over time, and actually one that's such that's inverse seasonality from the total sulfur flux. So the question is, how are we going to try to investigate this? And our answer is going to be through constructing a set of model simulations where we can vary emissions in a controlled way and examine atmospheric responses. So that takes us to the end of our introduction and brings us to our methods and model setup. Specifically here, we used kind of two types of models. First, just being a regular GCM or a general circulation model. We used NCAR's CESM2 model. Specifically, we used release CESM 2.1.5. It has a regular lat-long grid, and we were able to construct it with 56 hybrid sigma pressure levels. The other type of model that we used here was a radiative model. Specifically used this model called RRTMG, which stands for the Rapid Radiative Transfer Model for GCMs. This type of model is able to simulate atmospheric radiative interactions and is built into many GCMs like CESM2 as the standard radiation scheme. So I had to spend a lot of time, my first kind of year or two here, just looking at trying to understand how CESM and Earth system models work in general. And I think this slide that I tried to make sums it up pretty well, in that CESM is a model itself, but it's kind of composed of different component models where they look at things like atmosphere, sea ice, and ocean. Those are kind of the models that we tend to use in this building. But they're all able to essentially predict and solve these differential equations that are baked into them on their own, and then interact with each other through what's called the central coupler, where that kind of records exchanges in terms of mass and energy and momentum, and is able to communicate that with each other. So this is the basic setup for what CESM looks like. And then in terms of our research, what we needed was a modern climate configuration. So we used what's called a comp set, where we chose a prognostic atmosphere, river, and land model, where these ones are actually predictive and simulating over time. And then we have a prescribed ocean and sea ice models, where these models, they're not predictive. They're kind of feeding, or they're being read into by these climatological net CDFs. And then lastly, these two models are essentially absent, and they aren't present in our analysis. And that this is a modern climate configuration with model conditions set at a year 2000 climatology based on a 1995 to 2005 average. So kind of the next thing I had to look at once I figured out how to set up a model was trying to look at sulfur dioxide and sulfate aerosol in CESM. And that led me to CEDS, which stands for the Community Earth Atmosphere Data Set. And I think they do a good job of what I think of answering the who, what, when, where, and why in terms of radiative, or in terms of aerosol forcing, or in terms of aerosol amounts and emissions in these Earth system models. So looking at some figures that was by Rachel Hoseley in 2018, where they were first evaluating what this new set of CEDS data looked like, we were able to look at emissions of sulfur dioxide in teragrams of sulfur dioxide per year. And we broke that down by they were able to break that down by region, where we can see early emissions, tended to be from Europe and North America. That's that dark blue and light blue, where you can see, in 1750, there's no one in the world that's emitting this. We haven't, undergone any level of industrialization. But as industrialization begins, it was Europe and North America that, were the first to, be burning these sulfurous compounds, and really started to dominate, what the world's sulfur dioxide emissions were. But it wasn't until 1950 and afterwards, which we already saw, where Asian emissions from China and other Asian Pacific Island countries started to increase significantly, up to the point of present day, where these two make up over half of what's being emitted today. And then we can look at that again, this same exact data, but instead of grouping it by where the country that it came from, we can group it by the sector that it was being pulled from. And where we can see here, an overwhelming majority of these sulfur dioxide emissions come from energy transfer and extraction, along with some industrial-related emissions. Examples of these include burning coal, like we talked about, oil refineries, natural gas processing, metal smelting, and cement production. So that was looking at the kind of, the whole world in terms of that, and that kind of was a good start for me to say, what, I should maybe try to replicate this in terms of East Asian emissions, where again, we're looking at China, Japan, and South Korea. So that's what I did here. And I looked into the CEDS data, and I said, I want to look at what happens in China, Japan, and South Korea, and plot their emissions trajectories in terms of kilotons of sulfur dioxide from 1850 to present. And so yeah, here, this figure illustrates the time evolution of emissions from China, Japan, and South Korea, where we've highlighted emissions and the top 3 sectors that they came from at the following years, 1850, 1970, 2000, and 2006. These years, we decided from this graph, would serve as the varied emissions inputs for East Asia in our simulations. And the reason we chose these years, you can think of for like, here's the kind of the reason that we chose each year. 1850 we chose as a pre-industrial kind of baseline, where there are little to no emissions coming out of this area at all. 1970 serves as kind of twofold. One being the beginning of where we start to see this real upward trajectory in terms of emissions, especially out of China. But also we chose 1970 to be able to compare it to emissions in the United States, which actually peaked in 1970. We chose 2000 just as a simulation control. And then lastly, we chose 2006, as that was the year that China, which really kind of dominates this East Asian emission profile, peaked in terms of their emissions. Another thing we had to learn how to do was constrain the model meteorology. And to do that, we used something called nudging, where nudging is essentially forcing the model's meteorology to reanalysis data to ensure consistent conditions across simulations. And to do that, what we essentially did was we have these nudgeable variables of temperature, U component of wind, your V component of wind, and your specific humidity Q, and we nudged them to MERA2 reanalysis data that was based on a year 2000 climatology. And just seeing that in action, I actually have that here, where we can look at the evolution of some upper air temperatures with MERA2 data, where in this first monthly time step, this is before we've applied any nudging, and we have our model at showing upper air temperatures from 215 to 255 Kelvin, and then in the MERA2 reanalysis, we're looking at the same variable, but we have this large cold pool of air that exists over Asia, and so really we can see that these don't really tend to look alike right now. But that's at the first model time step before any nudging is able to be applied. When we step to the next time step, we can see that now our model is starting to constrain and be forced to what this MERA2 reanalysis meteorology is. And as we go further, we can see it tries to do a better and better job of doing that, of sticking to this MERA2 reanalysis data. And the reason we do that is because we're going to have our simulations such that we're looking at varied East Asian anthropogenic sulfates from 1850, which we saw are really absent, to 2006, which is really large signals of sulfate aerosol. And without kind of checks on meteorology, that could create diverging outputs. And while sometimes you want to use models to look at diverging output, here we're trying to constrain that so that we can have a large level of comparability between these different simulations. So I'll stick on this slide for a little bit, as it's just kind of our final review of the model setup and simulation design. Where here you can see in green I have all of the atmosphere, I have our atmosphere component, which is really kind of the main component model that we looked at as a prognostic component, along with some prescribed stuff, and where we're looking at how the simulations were set up such that China, Japan, and Korea in these 4 simulations that we set up, in the first simulation emit at 1850 levels, then at 1970 levels, at 2000 levels, and at 2006 levels, while holding everything else in the world at year 2000 baselines. That's pulled from that 2000 level climatology. These runs were ran for 10 years. 10 years, actually, they were ran for 126 months, where we discard that first 6 months as spin-up time, allowing the atmosphere to kind of readjust from initialization shocks to more realistic states. And that simple chemistry that we went over is actually the chemistry that these models follow. So I think it's also important to look at some caveats and assumptions in terms of what we were doing. Firstly being that we have these prescribed oxidants that we saw earlier. Those are going to be fixed at year 2000 levels. While this does ensure consistency across simulations, it may not reflect 1850, 1970, or 2006 conditions, and could lead to possible over or underestimates of sulfate production. Secondly, background aerosols are also fixed at year 2000 levels, such that we do that because these microphysical processes depend on background aerosol concentrations. And so we should note that having those at year 2000 levels while maybe having emissions coming out of Asia at 1850 levels may introduce some level of nonlinearity, especially in that low emission scenario that I referenced. And then lastly, looking at sulfate partitioning and processing, where we have to be aware that CESM2 partitions sulfates between interstitial and cloud-borne modes, and that processes like evaporation, cloud cycling, and wet scavenging are represented in the model physics, but the detailed microphysics are still not fully diagnosed. There's a level of parameterization that still needs to exist in these models. So that brings us to model and observation comparison, kind of the last part of our methods in model setup, where we're going to compare what we looked at or some of the actual output that we got from our model with some CloudSat and Calypso data that came out of a paper from this building, where we actually compare seasonal mean aerosol optical depth over the North Pacific, where we look at model emissions, or our model aerosol optical depth in that 2006 regime, and compare that to satellite observations that we were able to find from a 2006 to 2009 average. Yeah, Larissa.
Can I have a quick clarification? What role do clouds play when you're looking at these aerosol optical depth measurements? Does that include the cloud aerosol effects, or?
That's a good question. I believe that,
It's just direct.
yeah, I believe it's just direct, yeah.
Okay.
But yeah, so,
We'll talk about that later. Okay.
yeah. But so yeah, here looking at seasonal mean aerosol optical depth over the North Pacific, where we can see that in our model data, in our satellite data, both data sets show this consistent seasonal cycle, where we have greater amounts of sulfate and aerosol optical depth in the months like March, April, May, and June, July, August than we do in December and January. But at first it might not look like it's a really good fit to your data at all. But it's important to realize that in our study, we're emphasizing seasonal variability rather than absolute magnitudes. So the strong agreements that we see here build confidence in our model's ability to capture sulfate aerosol dynamics over the North Pacific. So that...
Could you have some hypotheses? Like, could be excess rain scavenging in the winter. It could be solar zenith angle and OH reduction in the summer.
Yeah, no, and we'll definitely get to that. Yeah, as to trying to attribute what this seasonality was. Yeah, we'll talk about that next. But yeah, we look at the first part of our results, which are investigating the seasonality in sulfate aerosols over the North Pacific Ocean. So the first thing I figured we would look at are time and spatially averaged climatologies. So here in this graph, we're looking at monthly average sulfate burden over the North Pacific Ocean, where we're looking at this sulfate burden is essentially the vertically integrated sulfate mass over this North Pacific Ocean in our 4 simulations. Remember, all of these have background simulations of the year 2000, but have varying East Asian emissions from 2006 to 1850. Here we can see, we have this historical increase and that North Pacific sulfate burden rises as we would expect across these varied East Asian emission scenarios. Just by that, I'm just saying that when we have 2006 levels coming out of East Asia, that does in fact produce stronger sulfate burden over the North Pacific Ocean, and so on and so forth down to real minimum levels coming from 1850. Also, what's striking here is that we have this emergent seasonality, where all these scenarios, regardless of what's coming out of East Asia, show a similar seasonal structure, where we have this buildup through January, February, March, the early parts of the year, to this consistent peak at April, May, and June, before then dropping off again in towards the later part of the year. And then here we have changes, looking at these changes relative to 1850. How this graph was constructed was from this graph, where we take this line, this pink line first here, is just differencing what the burden is over the North Pacific in the 2006 simulation from the 1850 simulation, this one, so on and so forth, of these differences from 2000 to 1850, 1970 to 1850. And so we do that because of this. You can kind of think of what the sulfate burden being as a function of just 2 sources. One being of 2 aerosol emission sources. One being our variable East Asian emissions, and then the rest of the world concentrations that are at this 2000 baseline. So when we look at differencing with an 1850 simulation, we notice they have some shared and then some different inputs to what produces that sulfate burden. But when we think about that aerosol emissions that come out of East Asia in 1850, it's essentially 0. So now when we difference these, we're able to, effectively remove what the background aerosols are, and then treat each of these curves as the background emissions, or as the background emissions cancel out. We can treat each of these curves as essentially the isolated incremental sulfate burden attributable to that year's East Asian industrialization. Looking at that spatially now, we can see this graph here where we're looking at the log ratio of sulfate burden between our East Asia 2006 and our East Asia 1970 simulation. And we're going to kind of, throughout the rest of the presentation, be mostly concerned, or be only looking at these differences between 2006, which remember represents our peak year of aerosol emissions, and 1970, which is a more modest time where emissions are just beginning to ramp up. So what do we notice here? We notice that East Asian emission growth drives basin-wide increases in sulfate burden, even though we're only changing the emissions within China, Japan, and South Korea. Even though we're only changing those, we're being able to see these sulfate burdens that are present across the whole of the basin of the North Pacific Ocean that, again, we have shaded in here. But that we also noted that we have our largest concentrations over the high emitting regions of China, and that outflow extends all the way across the North Pacific. And in some cases, just looking at the 2006 one alone, you can actually see sulfate aerosol, increased sulfate aerosol concentrations that make it all the way across the United States and into the North Atlantic itself. I'll also have you note that we had to look at this in a log space because some of the differences are so great that we had to we log transform it to look at both the great level of increase that happens over the emitting regions and the downwind areas as well. And then there's also some seasonal differences that start to pop up from this sulfate burden extent, where we notice when we look at April through June, which was kind of that, when we looked at that climatology before, the monthly climatology, we saw that during this time, that's when sulfate aerosols tend to be at their highest across all simulations, while in November and January, they're at their lowest. So yeah, here we're looking at spatial maps of these sulfate burden and their differences during this East Asia 2006 minus East Asia 1970 simulation, where we can see there's this large seasonal contrast actually, such that in the spring, the burdens are concentrated more over East Asia and extend strongly into the North Pacific, while there's a regional shift that happens in winter, where higher burdens appear over Southeast Asia and the Bay of Bengal, while the North Pacific shows reduced concentrations. I think that's shown, it's a little bit harder to see here, but within the seasonal difference, you can see that pretty well, where yeah, you have these higher emissions here that happen during this peak time, and those, but that the emissions area tend to move southward as time marches to the minimum months.
Could that be the effect of cold fronts?
It could be, yeah. We haven't looked too much at what the maritime meteorology is there. I think that would be a great next step for us to look at. But here, kind of going on to what you're talking about, is how do we connect this seasonality in emissions and burden? And to do that, we're going to actually consult another paper that Dan and I are working on with the postdoc in our group, Sagar Rator, where we look at the paper that we have in review that looks at an identical experimental setup, but this time focused on varied U.S. anthropogenic sulfates and North Atlantic burden and its radiative forcings. And in this analysis, we were able to perform regional budget analysis. And that's what's presented here. These sulfur dioxide and sulfate budgets in JJA and DJF over the US and the North Atlantic shown as differences between the 1970, which I'll have you keep in mind, in the US was the year of peak emissions, and US at 2010, which is kind of a more modern, very much lower emission scenario, and where these are all presented in terms of gigagrams per month of sulfur. And what do we notice here? We see that from that motivating puzzle slide, we saw that in the winter that's where we had larger SO2 emissions, and that was true in North America and the United States as well. So that plot showed that the winter had larger SO2 emissions, but here we're also seeing that when we difference between those emission scenarios, that winter also has greater changes in these sulfur dioxide emissions. But it's important to note that during this time, a lot of these, or in these winter months, that much of the sulfate that is created is converted through aqueous chemistry, And that aqueous chemistry tends to produce more short-lived sulfate aerosol that tends to rain out quickly. Versus when we look at gaseous production, we note that summer has a stronger OH chemistry, that being due to the seasonal cycle, or the seasonal cycle of the hydroxyl radical itself, which is dependent on solar inclination and water vapor presence already, that both of those have natural highs in the summer months and go down as time moves on. But then when we still try to answer why summer burden tends to respond more strongly to emission changes, I think what that can be answered by is this row here, where we say summer conversion compared to winter conversion is much more reliant on this dry production, this OH chemistry. So as emissions rise or fall, like they tend to rise in our East Asia emissions and then fall in the Rator et al. Paper, this pathway, this dry production pathway, amplifies the effect and creates larger seasonal changes in the summertime when these OH chemistry is dominant, or not dominant, when it's relatively dominant compared to winter OH chemistry than it is to wintertime. So that brings us to also some implications for seasonal radiative forcing over the North Pacific Ocean, where this part, we see now that we have these modeled signatures of increased sulfate aerosol that has a seasonal structure itself over the North Pacific Ocean. But now we're trying to see, how does that actually play out in terms of radiative forcing? So to do that, we had to set up a flux perturbation experiment using RRTMG, which is that rapid radiative transfer model for GCMs. So what we did was we used this paired call method that I'm about to get into, that we based from the GON papers out of PNNL, PNNL being a DOE lab that tends to look a lot at aerosol chemistry and stuff, and aerosol radiative effects. And so the idea here was to run radiative transfer experiments under 4 controlled atmospheres, each with or without some combination of sulfate aerosols, which is our aerosol of interest, and clouds themselves. We can see those 4 configurations right here, being a total sky configuration, a clean sky configuration, clear sky, and a clean clear sky, where they have some different combination of clouds and sulfate aerosol and background aerosol. And we'll visualize that in the next slide. But essentially, comparing radiative flux perturbations between these configurations allows us to separate sulfate radiative impacts into distinct effects. So I think this table is nice, but I think it's better to visualize it like this, where here's kind of our 4 copies of our atmosphere. First, we have this base atmosphere that has everything in it. It's unperturbed, where we have our sulfate, our varying sulfate aerosol, these 2,000 level background aerosols, and then whatever cloud presence was there. Then in our clean atmosphere, that's essentially copied over, but the presence of sulfate aerosol have been removed. In the clear atmosphere, it's another derivative of this in which we're taking away the clouds, making it clear. And then in the clean clear atmosphere, that's the final combination where we've removed both the clouds and the sulfate aerosol themselves and leave only what the background aerosol is. So this is the setup of what those 4 atmospheres are. And within that, we then run these radiative flux perturbation experiments where we send down some, RRTMG, sends down some measured amount of radiation from the top of atmosphere and then measures what's returned and takes its, flux to get some sort of net shortwave flux at the top of atmosphere under 4 different configurations. Where, what we send down is always the same, but what we get back up is different, where we can see, we have, without the presence of these sulfate aerosols in this clean atmosphere, where these sulfate aerosols themselves are directly scattering, we have less returned, in fact, making then a greater amount of net, flux at the top of atmosphere. And then in the clear atmosphere, we do the same thing, where we get rid of the clouds, and those clouds are highly, highly, reflective. So we return even less at the top, and then lastly, in the clean, clear atmosphere, we send down the same amount of radiation, and then figure out that we don't get very much back at all because we've removed essentially the scattering and reflecting abilities of the sulfate aerosol and cloud themselves, and take that difference. So, but this is still just kind of looking at what these net fluxes are at the top of atmosphere. We can then take that down and look at it here, where we can take these net flux, or these net fluxes at the top of atmosphere and compose those into different radiative effects. When we want to look at the direct radiative effect, we look at the net shortwave flux at the top of atmosphere in our base atmosphere and difference that with what we found in our clean atmosphere. When we look at cloud radiative effects, we take what was in our clean atmosphere and difference that with what was found from our clean, clear atmosphere. And then lastly, when looking at surface albedo effects, that's just going to be what we're looking at when we look at this net flux of clean, clear at top of atmosphere.
And then there would also be an interaction between the clouds and aerosols too. There would be another one if you wanted to add them.
Yeah, there's.
That's,
Or is that?
this is a good question. It's one that I wrestle around. So maybe explain how that in the cloud radiative effect.
Yeah, so in the cloud radiative effect, so that's taking differencing what the clean and the.
Why does that only include clean? Yeah, is it different if you do the?
Yeah, so what?
Still.
So what we do here is that one's a difference between clean and clean clear. So that one, you can see the commonality between both of these is that we've removed what the sulfate aerosol is. The cloud that's still there is always going to be, we've removed where that sulfate aerosol is. The cloud that still is present in this clean is the cloud that's present in the base atmosphere. So when we difference these clouds that were still formed by or formed under the assumption of having these sulfate aerosols themselves, differencing that will tell us what the cloud radiative effects are that have been generated from these sulfate aerosols. Does that make sense?
So just to clarify, if there's a change in CCN due to aerosols, that is retained in the clean simulation. The cloud droplet number concentration is not adjusted between the base and the clean. So to get the pure cloud effects, it's still, which is something that
Okay, but the base minus the clear is not necessarily as the clean minus the clean clear, right?
Yes, I think you're correct there. But really what we're just looking at is the only ones that we're actually looking at here. We have the ability to decompose this further, but what we're just going to be focusing on is base minus clean and clean minus clean clear. Go forward again. So we did all this. All right, but still, we'll do one more step of decomposing this, where these are still, the direct radiative effects. We've yet to get that to, or radiative effects. We've yet to get that to radiative forcings. And to do that, we need to then, run these net flux perturbation experiments under two different simulations, where let's say we look at, these were the measured radiative effects from our simulation where we have East Asia emitting at 1970 and the rest of the world at year 2000. And then we look at another one where we say, here are the radiative effects from looking at a simulation where East Asia emits at year 2006 and the rest of the world at year 2000. Finally, what we do is we can difference these measures, or where we difference, what these net fluxes were across simulations to produce, what the forcing was and look at how these changes have essentially propagated over time and across simulations. So then we can follow those down and see, what output did we actually get. So here are these, climatologies or climatological forcings from the 2006 minus 1970 North Pacific total radiative forcing and components, where we have this, surface albedo forcing, direct aerosol forcing, cloud aerosol forcing, and total aerosol forcing. And what I'll have you note is that they all have some sort of seasonal structure. And that seasonal structure tends to be one that's exaggerated or at some sort of maximum or minimum during this time of April, May, June. We see that here, April, May, June, this time April, May, June. This one actually shifted back between March, April, May. But that this was the time that we also saw previously when we were looking at our first part of the results that, this is where we have the largest amount of sulfate aerosol in the basin itself.
I'm sorry, what is the cloud aerosol forcing? You had cloud forcing in the last slide.
Oh, yeah, sorry. Cloud aerosol, the pseudonyms.
Okay.
Yeah, sorry, same thing. Cloud aerosol forcing and cloud forcing. So they all have, this level of structure themselves, but I think that this graph can be a little bit misleading. When you plot them all together on the common axis, when we plot them all together, you can really see that the total radiative forcing, which is just the sum of all three of these, is really just dominated by the cloud forcing. Over time, it's actually 98% of what we see here is due to that cloud forcing. So yeah, these are looking at these geospatially and temporally averaged climatologies of the forcing components, where we see that all radiative forcing components display some sort of seasonality, but the forcings we have to know exist at a relative scale, where the cloud is very dominant to the direct effect, but the direct effect itself is also very dominant to the albedo.
And so your interpretation of this is that this is the CCN effect on the clouds. Is that, am I following that right? That's why.
Yeah, and we'll talk more about that in just a second. But yeah, the main takeaway here is that the sulfate cooling that we saw here over the North Pacific is overwhelmingly controlled by this aerosol cloud effect, or this aerosol cloud forcing. And when we look at that throughout space, here's that same graph that we looked at earlier, where we're looking at East Asia at 2006 minus East Asia at 1970 during these peak months of April through June and these minimum months of November through January, and looking at what their seasonal difference was. Where we say, these peak months tend to have, higher concentrations over the North Pacific and East Asia, as we see here, and during the minimum months, those concentrations get shifted southward over southern China and Southeast Asia. When we compare that to what the maps of the direct forcing are, we note that the direct radiative forcing patterns largely follow the same spatial footprint as the burden layout, and that should make sense to us because these changes aren't getting propagated much further than where the plumes are heavy themselves, where we have the same dipole where during the peak months of April through June, the forcing is greater over the North Pacific and East Asia, whereas the direct radiative forcing that comes from the scattering ability of these aerosols is greater more to the south in the Bay of Bengal and Southeast Asia during these November through January minimum months. And then when we compare that to the cloud radiative forcing, which we've noted really dwarfs the direct radiative forcing component in terms of its strength, when we look at that, its spatial patterns as well, we note that not only is there much larger magnitude, there's also a much broader spatial extent than the direct radiative forcing. That direct radiative forcing seems really just present over where the high emitting areas are, and then somewhat over the North Pacific Ocean itself, versus the cloud radiative forcing actually tends to be highest actually over the ocean itself, and can really spread during many places. And that when we take a difference map, we can see that we produce a consistently negative cooling pattern with a coherent basin-wide cooling signal. So, kind of talking about what you were talking about, Larissa, is trying to untangle what these cloud radiative forcings are. And this is kind of just first attempt analysis, but looking at again similar differences between our East Asia in 2006 and our East Asia in 1970 simulations, looking at some variables that more relate to the Twomey effect versus some that relate to this Albrecht effect of suppressed precipitation. And we can see that over East Asia and into the North Pacific, our varied sulfate emissions drive increases in cloud droplet number concentration and cloud liquid water content, kind of exactly in those same areas. And also that we get these acute responses in terms of cloud gain, in terms of low cloud presence right over that same area, and then medium cloud presence where it's a little bit fuzzier, but I'd still argue that this seems like an expected signal. And when we compare that especially to these sparse or noisy responses that we have in simulated precipitation differences, I don't really see anything here. So that was kind of it for looking at the implications for seasonal radiative forcing over the North Pacific, and I'll lastly kind of look at what some broader implications are in the ongoing work. So in terms of synthesis and implications that we can take away today, there's kind of three families of them. First being what our science takeaways are. First being that we had seasonality from steady emissions. That's going back to that motivating puzzle slide where we saw these steady and tightly clustered emissions from East Asia producing a historical and growing seasonality in the North Pacific sulfate burden. We now think that we can more so attribute that to gaseous chemistry and transport than what the emissions were themselves. And then looking at broad spatial reach, where we saw that emissions from East Asia, even though we locally produced those, that produces sulfate aerosol masses broadly across the North Pacific Ocean, and that there's a cloud dominance in radiative forcing. And we saw that modeled cloud radiative forcing produces nearly all of the total radiative forcing signature. Then in terms of climate, it's important to remember that these sulfate aerosol effects are comparable to greenhouse gases, where we saw regional peak sulfate forcing or cloud sulfate forcing exceeded this -2 watts per meter squared. That puts it on par with changes in radiative forcing from carbon dioxide from pre-industrial times to present day. But still, these aerosols, unlike these well-mixed greenhouse gases that have long residence times, are highly variable throughout time, space, the sources that they come from, and all sorts of atmospheric processes that go to having some sort of chemical transformation or removing them. And so they still remain, one of these largest uncertainties in Earth's energy balance. And then lastly, in terms of policy or future trajectory, it's important to be aware that air quality improvements matter. And currently, data suggests that, or data says that sulfur dioxide emission reductions in China have been, or there have been large reductions in sulfur dioxide over China, which that does matter, but it is also true that this is removing what these masking effects of sulfate cooling was. And that this can have unintended climate consequences. And that while cutting aerosols improves human health, it also is unshielding the underlying greenhouse gas warming signature and potentially accelerating ocean heat uptake and regional climate change. And lastly, that there's still a need of research for this. So understanding aerosol cloud interactions, especially is going to be essential for predicting near-term climate evolution. And when we think about what records that we have back and say was this warming signatures that we've seen throughout history, have these been somewhat masked by variable and now declining sulfates themselves? So but there's a research need for this, especially as emission trajectories tend to diverge globally. Right now, the U.S. is very low. We have very clean air in terms of sulfur dioxide. China trying to get there themselves, but there are other countries that are on the rise in terms of what they're producing right now. So, lastly, I talk about some our ongoing and future work, which will mostly talk about some of the experiences that Dan noted that I had at Oak Ridge National Lab this summer, working with the DOE and the DOE's model of E3SM, doing some machine learning stuff there. And this kind of funny graphic. This is not really me because I like linear algebra, but and then doing some mixed layer modeling as well. But kind of the first thing, and this is actually what I started on with this project, is comparing these burns and forcing with the North Atlantic study that we have submitted with our paper Rator et al., where we have this mirrored case now to investigate if the seasonality mechanisms in burden and radiative forcing are region specific, or if they are more general, and that we can see a similar story happening from these U.S. emissions that peaked in 1970 and have declined since. It's also valuable because in the U.S. there's a different emissions history, and we have more available observations for evaluation. When Sagar was doing this, he was actually able to use improved ground monitoring sites and as opposed to satellite data, and that had a much closer it still showed the same seasonal cycle, but it had much closer absolute magnitudes. But also, this would just be great for building this cross-basin understanding to understand how regional emissions project onto downstream ocean climate impacts. Also, you're looking at this from a cross-model perspective, where the work that we've just presented was all throughout CESM, NCAR's model, but also looking at this in E3SM, where we're replicating the same framework in E3SM. That's a lot of what I did this summer, where we're looking at these East Asian sulfur dioxide emissions and U.S. sulfur dioxide emissions perturbed across historical scenarios, where we use these same diagnostics for burden and radiative forcing. But there are some key differences between what's going to be in CESM and what's going to be in E3SM due to different aerosol module configurations. CESM uses something called MAM4, whereas E3SM has been updated to use MAM5 or MAM7, which partitions aerosols differently in terms of different size bins and where they can exist in the model physics. There's also distinct cloud microphysics and convection schemes. In E3SM, we had to use a 2010-based configuration as opposed to our 2000-based configuration. And also even just basic simple things like there's different resolutions where E3SM uses this squared grid mesh rather than a regular lat long grid. The other thing that I worked on a lot at Oak Ridge over the summer was, replacing these paired RRTMG double calls with some sort of machine learning emulation with some feed-forward neural network. The motivation for doing this is that these paired RRTMG calls are accurate, but they're computationally costly, and such that trying to use these for large ensembles or long simulations are prohibitive. And the fact that you can't go back and use them on existing simulation as well. So the approach for this was we had 60 CESM ensemble members, which we used to have globally linearly scaled sulfur dioxide emissions from everywhere in the world. And we used that as kind of our base data, where we ran RRTMG on them. They were each ran for a year and a half, where we take that first half a year and discard it for spin-up time. But we used RRTMG on these, where we can use those double call outputs that we went through as what the training target is for our machine learning emulator. And what we can also use is their standard model output, like sulfate burden, cloud fields that we saw, and other state variables as predictors in this regression tasked feed-forward neural network. And yeah, the goal of this is to train a fast neural emulator that can reproduce radiative forcing components and try to maintain some sort of physical consistency while substantially reducing the computational cost of that. And lastly, is linking aerosols to ocean responses through mixed layer modeling, where this is some work that Dan is working on, where we're trying to connect atmospheric forcing like sulfate-driven radiative cooling to ocean temperature responses. To do that, we applied a mixed layer model to simulate surface heat fluxes with ocean heat content, with the goal of attributing these observed and simulated sea surface temperature variability trends to a combination of some radiative of this aerosol forcing and ocean dynamics themselves. Lastly, I'll just go through some acknowledgments. First of all, just to everyone in here, I feel like, especially with any professor, I've probably stopped by your office once or twice just to ask you a question out of curiosity. Also, especially to anyone that's pictured here, my best friend Jonas, this is pets back at home. This is Carissa's nice cat Alfie, some dogs at home. Big thanks to the DOE and people I got to work with there, specifically being Salil Mahajan, who took me in to work for 3 months at DOE at Oak Ridge, which was just a really great opportunity and something that I don't think not many master's students got to have. Also, you can't see me, but I'm the tallest person in the back here. This was me at another DOE event at Berkeley, where I got to look at how E3SM is run, and that was really fun too. I did my undergrad here. Here are some of friends from undergrad in this department that have gone on to do some cool stuff. Big thanks to Sagar and Dan. I only had like one picture of us, and it just happens. Although I like it though, because it's we're looking at some sort of math on a board where we're trying to probably look at these decompositions of radiative forcing. So huge thanks to Dan and Sagar. Dan really kind of let me walk whatever path I wanted to walk in terms of this research project, and really kind of dig into the nitty-gritty of modeling and being able to run my own model, which is again something I don't think many younger students get to do. So really appreciated that. Friends from grad school. I see a lot of you here right now, and this is a picture of us at Waffle House from I think it was spring break or something. And then also just my family, my mom and my dad and my sister, always really great supporters of me. And with that being said, we'll get into some questions, and I'll let the slide play again because it is very pretty.
All right, Jack, I'll let you call on folks, but as usual, questions from students, and then we'll move on. So.
Yeah, I'm sorry, I don't know the name.
My name is Noah.
Noah.
Thank you, Jack. That was an awesome presentation. One thing I thought of, because we wasn't talking so much about chemistry, is if there's like an opportunity to look at like acid rainfall over the ocean as part of this study, and if that's something you guys consider at all.
I think that is interesting, but actually this kind of all started by looking first at sea surface temperature variability itself and seeing, can we link that to some sort of radiative forcing? So with kind of keeping temperature and radiative forcing in mind, that acid rain never crossed our threshold in terms of things we can look at. But I know it's a big problem, or not a big problem. I know it's a research area as well. My chemistry is probably not up to par in terms of that, but it would be interesting to look at.
You're right. Are there measurements of one of the issues we run into is there are measurements over land, but measurements over open ocean are really hard to come by. Are there measurements of sulfur in rain over oceans? Good question.
Evan, I think you had a question.
Yeah, I think you hinted at this a little bit, but there's some work that implicates some of this radiative stuff in the aerosol forcing in what we normally think of as low frequency internal variability that we see in the climate system. My question is, how does your work fit into that, and do you think that the results that you saw are large enough to have a substantial impact on that sort of thing?
Yeah, that's interesting, and I think it kind of gets to something that I had in an earlier version of this presentation where we kind of looked at, when we talk about low frequency forcing, that it's interesting, like when we saw on this loop, the satellite loop, there was like, volcanic eruption, that, that's like a high impact event that, might make a, big splash and might be resolved or be, resolving the atmosphere for a while. But these more anthropogenic based emissions are, kind of continuous and every day, so they do fit into that low frequency, forcing drivers. And we haven't looked too much at, trying to, I guess, look backwards and say, like, how does this fit into what has, or radiative forcing historically? But I think that would be an interesting place to, kind of take results, or at least thinking that's gone into here, and, look backwards with it.
I think what you did would be interesting for that, because you're nudging the atmosphere, you're going to cause the atmosphere to be like roughly in the right state for what we actually observed for that sort of forcing. But then you could actually see how much more radiative forcing is due to the aerosols from your perturbation experiments.
Yeah, no, that
would be really interesting to see if that value is on the same order as the value between like positive and negative sign.
Yeah, I guess another thing you could do that is, a lot of times of the differences that we did with that 1970, but we do have that 2000, control simulation that can somewhat be used to, say like, well, what was the radiative forcing that we can best estimate, that existed at grid box A, like, and then compare that to, the ones where we have more variable emissions. Yeah, Rudra?
So great talk, Jack. I have two-part questions. The first part is that have you looked at the vertical distribution of your sulfate loads? And if yes or no, do you see similarities between your two regions, how that load is distributed? Maybe trying to guess how it is transferred, maybe it's the surface winds or just the winds aloft through jets that causes this seasonality or something?
Yeah, that's a good question. I think it's probably important to remember that most of the sulfur that we're looking at here is from ground-based emissions. So just I haven't looked at it yet. I know Sagar has done some of looking at the vertical distribution of aerosol. And it mostly looks like it's in the lower troposphere. And I think it takes these some large events, even these stacks that are hundreds of meters up to 300 meters in the atmosphere. It's not producing enough vertical resolution to get it to a place that I would imagine that it's really being transported by jet-based winds. But
yeah, I'm going to just counteract that. There is a big difference in between say summer and winter as well. There's the summer you're locked in that area. You actually are getting that aerosol in the free troposphere. If you look over the locally, there still is a maximum near the surface locally, but once you're over the North Pacific, it's a lot more uniform, and that vertical distribution can play a big difference in the radiative impacts if there's clouds underneath it versus not clouds underneath it. And so you're right. Locally, it's mostly near the surface, but once you get downstream, it is whatever.
Yeah, and that's another point that, like, in terms of vertical distributions of things, what we've started to actually look at is not so much, or it's important to know what the vertical distribution of the aerosol itself is, but especially the vertical distribution of the aerosol in relationship to the clouds themselves. And you can get, vastly different radiative forcings, whether, like, you have aerosol that's above cloud or below cloud. Because essentially, if the aerosol is below cloud, it's not going to be interacted with at all with this radiation. Yes.
So you use the SEDS emission inventory.
Yes.
Can you talk more about how the seasonality is imposed, especially for the much earlier or something?
Yeah, so SEDS, to my knowledge, SEDS is, the Community Earth Atmosphere Data System, and they try to take, they take self-reports in terms of where those aerosol emissions come from. In terms of China, Japan, and South Korea, the bodies that submitted to SEDS there in China was a place called MIIC. In Japan, it was JPCC, and in South Korea, it was the National Institute of Environmental Health. And so it's kind of it is an interesting thing where it's like you don't have, especially back then, you don't have absolute measures of where these aerosols are coming from, and again, it's kind of based on an honesty policy in terms of what gets turned into SEDS, and that was something that I feel like early on I had to learn about a little bit in terms of like not all data is going to be like easily available. That's another thing that makes kind of comparing this to the first paper that we were looking at with emissions over the United States, where we have much more readily available measures of aerosol themselves. Yes. Yeah, John?
Go ahead, Larissa.
Or Larissa?
Okay, I'm just curious, like, interesting talk, you did lots of cool stuff. I'm just curious about kind of the underlying hypotheses that led you to go this direction and set your simulations up. Was there like something about like the seasonal cycle of the SST and
that was exactly,
or something like that, or?
Yeah, that was exactly that. And I tried to kind of say that when Noah asked about the acid rain, that what kind of motivated this was looking at trends in sea surface temperature, and that there have been seasonality in ocean warming over the North Pacific Ocean, and trying to see if can we tie that back to some sort of radiative forcing rather than just internal ocean dynamics themselves. And when we looked at what signatures were over large timelines of aerosol emissions, they started to seem like they tracked pretty well. Where it's at when things started to warm a lot, we maybe had decreased emissions, and so removing that shielding effect. But that's kind of what Dan has looked at, and I think actually Dan just gave a talk about that yesterday.
Yeah, I'm not here. Yeah. So I'll talk about that hopefully in spring, but it was motivated by looking at trends in SST. So right now the mid-latitude oceans are warming somewhere between 50 and 100% faster in summer than winter, which is consistent with the sulfate aerosol forcing.
And so
When you put all this is the hypothesis. When you put all this together, the hypothesis that the sulfate aerosol seasonality is leading to that warming, that hypothesis is wrong. So I will be happy to talk to you about that at some later point, but it's a really interesting story.
Okay, but this was supporting that hypothesis, this analysis.
This was what the hypothesis was based off of. That's what we got funded based on that hypothesis. And in the course of the work, we proved that hypothesis is not correct. So
That happens.
it happens.
I'm going to do the
Yeah,
she's
yeah,
a
and
aerosol person.
Yeah.
Nice talk. So you showed that there was a strong seasonality in the and then you also showed that there was a strong seasonality in the cloud, in the indirect forcing, that seasonality was offset. Do you have hypotheses for what that is? Do you think that's because of that seasonality of the stratocumulus in that region? Or?
That's a good question. Again, it kind of feels like there's so much that I could look at in terms of what this aerosol, or in terms of what this climate model output is. That is something that I do want to look at, because you're right, it has that 1 month offset to it. I wish I had a better answer for you, but it was something I would like to look at. Do you have any thoughts on it, Dan?
I think it has to do with the aerosol per aerosol, the cloud radiative effect of it. If you didn't have to take into account zenith angle and everything else, the swarming effect would be much stronger in winter than summer. And I think that's something you need to look into. And so that shifting comes from, so, look.
Yeah,
John,
last
you
one,
wanna ask
last one.
question
Yeah, I have
here?
a really quick
Yeah.
one, I hope. First of all, great talk. Secondly, congratulations to all three of you for having proposed A and found out that A was wrong. That's how science advances, of course.
Yeah.
So that's fantastic. Jack, in both cases, I think you mentioned an Albrecht effect, with which I'm unfamiliar, so I hope it's not a naive question, but the cloudiness that you attribute, low clouds in the eastern Pacific and then downstream in the eastern Atlantic, are conspicuously downstream of storm tracks in the cold season. And so I'm wondering, how does the aerosol get back down to the boundary layer? Presumably it's lofted in the cloud shields of extratropical cyclones that are blowing up off the coast of Japan or off the coast of the Carolinas. How does it get back? Does it just settle, or is there an organized, systematic transport downward?
I would imagine there's some sort of turbulent mixing that will take it vertically anywhere. But also in our in our simulations, one thing that's, parameterized is the cloud's recycling, where I think it's like, every time step, essentially what 1/3 of that cloud was, we say, that gets evaporated. And I don't know if there's, separate dynamics for how, molecules or masses that are in free air versus, within a cloud body itself get treated differently in the model. I think so far, I'm sure they also can be subject to, things like downbursts or whatever, but we haven't looked at that much. And I don't know exactly what, sort of analysis I would look at for that, but it is an interesting question.
Okay, thanks. We can talk about it another time.
All right, we've held you long enough, so let's thank Jack one more time.